How you guys doing today? Good. I can already feel that the spring break is coming. But let's go and start. Then we'll hopefully we can finish up the chapter 6 and 7 by this Friday. But anyway, you can go ahead and start. So last time we talked about the cis and transform. So the cis and trans simply for your alkene compound that has this type of structure. Let me give you one example actually here. Okay, we have this one. Okay, so those are different because you have a double bond in these two carbons here and here. As you know, it cannot be rotated because the double bond between these two carbons. So we kind of differently name these two by just putting this one is the trans and this one is well, you can just go this way. Okay. So this is a cis. Okay. So in this case, if you have the trans, because you have the R groups, two groups on this double bond has the opposite side. So it'll be here and you're across from where you have the double bond here. But in cis form, those two are located in the same side, top, bottom here. So then we connect for this cis, and this is the trans. It's just simply because of the double bond. We just can rotate it. So we wouldn't have a problem if it's just a single bond. We can easily rotate. It will be just the same compound. But because of this double bond, we try to name those two compounds differently, trans and cis. So this is what we did last time. Okay, and then let's talk about a little bit more tricky. Okay, so if that is the case, we have I'm just going. Okay. We have a E and Z configuration system. So if you have a double bond here, okay, and then you have this one. This one, okay? So now you have obviously a bit more complicated than before. You have two alkyl groups over here. You also have a halogen groups over here, and there's nothing but just the hydrogen here. So in this case, what you can do is you try to break in half, like a left and right, and then make sure you have different groups on each carbon on this double bond. So the hydrogen methyl group like and halogen methyl group like. So they're all different on each carbon here when you break this in half. And then only thing you have to do is you have to prioritize. So you have to put the priority on each groups on each carbon here. So when we do the prioritizing those groups on each carbon, we also do Canning-Gold preload convention. Do you guys remember this? When we tried to do this for the RS configuration, right? For this one, for E and Z system, we can say this one has the prioritizing these two groups by following the Canning-Gold preload convention as well here. So meaning, from this carbon here, this is only one hydrogen, but it has carbon here. So carbon is atomic number wise higher than hydrogen, right? So this is the higher priority than this one. So there will be only 1 and 2 on both sides. So this is higher, this is lower. So you can actually say it's a higher and lower. So you only compare the groups on the same carbon here. Okay? So it will be just 2. Same thing over here. So you have a bromine which is a lot higher in atomic number. So this will be higher priority there. Okay? This is lower. Okay, and then now you're done with the prioritizing, and you just do the same what you did for the cis and trans. So if you have a higher groups and higher groups on the or lower and lower in the opposite side, that is like a transform, right? And then we're gonna do is E configuration. Okay. So if it's on the higher, and lower on the opposite side, that's like a cis-like kind of configuration, but a bit more complicated because you have more than two substituted groups on this double bond. Then we use E and G, which is much broader concept to define this type of the structure in alkane. So higher, lower, opposite side. It's like a transform, but a bit more complicated. Then we're gonna just put it in E configuration. Okay. All right. So so this will be E, and will be 2 bromo 2 butene. So it'll be 1, 2, 3, 4. So it'll be butene. But you can have this one is a 2 and 3. So it'll be 2 butene. But you have a bromo groups on carbon number 2, so it'll be E 2 bromo 2 butene. Okay. But the most important thing is you just need to know how to put this in the E or Z configuration if it's in this type of form. Okay. Does it make sense? Okay. All right. So let's try one more. About this one. Maybe this is a okay. So in this case, once again, I'm gonna do the same. Okay. I'm gonna do the same. So you have this two groups here and here, right? So obviously this will be higher, right? Good, right? Okay, higher, because bromine is higher in atomic number than carbon here. Okay. Higher, and this is lower. So this is done. Now we have this one and this one, which is the same carbon, right? We have the same carbon here. But it's also same with the Cannigo-Purity law. If you have a tie in atomic number, you go further. Okay, so you have a. So I didn't draw, but there's a hidden hydrogen over here, right? Because it's double bond of 1 and 1. So it'll be hydrogen, carbon, hydrogen, carbon, hydrogen. And this is just hydrogen. Okay. So in this case, you also have a higher and lower. See, the tie in carbon, you go further from there. It's the same, literally the same as the Cannigo-Purity we use for RS configuration. Makes sense, right? Because it's just the same thing we're doing here. And then, yeah, we're done. So when you put it on the double bond now, so you have a higher and lower on the same position, right? Top and bottom. So they will be in like a cis form is Z. Okay, Z. So E means entadigen, is the German. It means it's not crossed. Z means Jusamen is on the same side, together actually in German. Do you guys speak German? I just heard that, but I'm not sure if it's right. But anyway, so that is the case. So this is one thing you can do. Okay. So then this will be what? This is the longest carbon chain you can find, including two double bonds over here. Okay, 2 double bonds over here, and then this will be then pent, right? Pentene. But you have 1 and 2. So 1, 2, 3, 4, and 5. Okay. So in that way, you can include 2 double bond, which is most important. you can go this way because you can include this double bond if you go this way in the shorter end. So then there will be two double bonds, right? There will be two means di, E and E. Once again, when you have the two, pentadiene is kind of weird to say, right? So pentadiene, that sounds more fluent. And then you need to look at this 1 and 2. Okay, so we have 1 and 2 and 3 and 4. So it'll be 1, 3, pentadiene. You can also say penta 1, 3 diene. That's okay. You remember this, right? Doesn't matter. And then you just need to add these two groups over here, right? So it'll be 4 bromo, 3 methyl. I just did it this way because it's D and M. Okay, it's 4 bromo, 3 methyl, 1, 3 pentadiene. And you guys may wonder, why can't you write the carbon from here? 1, 2, 3, 4, 5. Because I wanted to give a lower number for these two positions, which double bond is more important. Makes sense, right? Yeah. So then most important is G. So G 4 bromo, 3 methyl, 1, 3 pentadiene, or you can say penta 1, 3 diene. Okay. Okay. So on your exam, don't worry about it. I'm not gonna put how you can name this compound. Okay, don't worry, there'll be too much. What I'm gonna ask you for the exam is, if it's E or G system, find out. Okay, so you don't have to know how to name the whole thing, which might be too complicated, which I think is too much. But the most important, you should know if it's not can be easily defined by cis or trans. You at least need to know. Oh, I need to use E and G system instead now, and this is G. Okay. Makes sense, right? Okay, so it will be that. Yeah. So, oh, just one more thing. So you guys know this is double bond where you put the G system in here. Do you know why I didn't do on here? Do you see I didn't put E and G over here, which you also have a double bond here. Okay. So what it looks like here. This is a whole R group here. There's a implied hydrogen. Right? This is double bond here. This cannot be used for E and G because of these two. You have the same groups on this carbon, right? In that case, it cannot be cis and trans or E and G. Do you know why? Because if it's the same compound, the one carbon, the double bond, but the other possible scenario, you just flip it. It's the same thing. So that's why it cannot be used for E and G, just this one. They're all different on these two carbons. Then okay. Makes sense, right? All right. All right. So the next one. Okay. Oh, this is also important. So this is trans. You have a cis. You can see that I'm not drawing the carbon hydrogen here, but you can see this is trans. Yeah, you see this implied hydrogen here and all there, but this is trans and cis. Okay, so can you guys guess which one will be a bit more stable than the other one? If you have a trans and cis form here, which one do you think will be more stable, like a spacing problem wise? This is slightly more stable than this one, slightly. It's simply because of the you have two kind of bulky group on the same side, right? That's what I mean by the cis, right? On your double bond, if it's on the same side, it's a cis. So usually cis form is slightly more unstable than trans because they need to compete for the same space. Okay, so those two bulky groups have to compete for this limited space on the same side. So usually trans form is slightly bit more stable. So if you look at the energy diagram, for these two, the cis form will be slightly started in the high, and the transform actually use slot in here. Eventually you get the same product, butane, but the cis form is slightly higher than trans, means it's slightly more unstable. As you know, if it's lower in the energy levels position, means it's more stable. So this is simply because of the spacing problem. They may experience a little bit of discomfort when you have those two R groups are competing for the same limited space. Okay, so it's about 4 kilojoule per mole. It's that kind of difference there, but it's not so much. I think it's just about 20 kilojoule per mole. This is you don't have to know the number, 116, but just very small. But still, there is a bit of change in the stability of these two. Okay. Makes sense, right? I just move on, but just good information to make a point. Okay. All right, so the let me think. Okay, I may give you. Okay, let's do this first. I'll probably give you the problem later. So if you have this one, you have a carbons in here, and then you have this form. Okay, you have this form. This form, okay, and then we have this form. Oh, I should have a spacing problem. Okay, and then this form over here. So this symbol I mean by the stability. So if you go from the left to the right, you can expect the higher stability. So obviously this is the least stable form among those 5, but this is second, and this is the second most stable, and this is the most stable one. So the only difference that I made from those arcing compounds is how many R groups are attached to the carbons in the double bond. That was it. So R group is just like any alkyl groups, like any carbon with the hydrogen groups attached to carbon here. But here is only one R group, and they're all 3. There are two, either same carbon or different carbon, but 2 R and 2 hydrogen, 3 R and 1 hydrogen. Oh, sorry. 3 R and 1 hydrogen and 4 R's. So in this case, we kind of name this mono-substitute double bond, or alkene, or di-substitute, tri-substitute, and tetra-substitute. Okay, because it just numbers of the alkyl group attached to the carbons in the double bond. Okay, so then if you have more numbers of R groups attached to substitute on your alkene compound, the double bond, that makes more stable alkene compounds. Okay, so I'm going to explain why. So the first reason is the hyperconjugation. So conjugating simply means they're kind to combine into the one. Okay, but it's a hyper because it's not happening in a normal fashion. What I mean by that is that whenever you have a double bond over here, meaning you have also the pi bonds over there. Okay, you have a p over there. If you have any neighboring carbon with a hydrogen, do you know this one will be all single bond here, right? If it's the methyl group here, and then you're going to have somewhat 109.5 degree, like not always same, but we're saying averagely speaking, here and here, right? So when we actually draw this a little bit more precisely. And if you look at this one on the same plane, this will be actually looks like this. Okay. You know, so it's not those three are kind of on this side, but look at this 3D. Okay. So you have the carbon hydrogen bond kind of a conjugate with this one over here. Okay, so that makes your double bond in the compound that more stable because they have a similar electron density reason that they can sometimes conjugate with. So which is they cannot do with just hydrogen on it. But if there's R group with the hydrogen, they sort of have a hyperconjugation to there, so they can have a more stable. Okay. Yeah. So does it make sense? Okay. Because of the carbon, the hydrogen, there's a single bond, right? And they kind of located in this way, because it's tetrahedral structure. And if it's nearby the double bond, it should be kind of easier for them to be conjugated on to them. Okay? So that's why. So the thing is, that explains why you have more R groups there, that makes more stable. Okay? Because the hyperconjugation. Okay? Actually, you don't have to know for the exam, but I'll just explain. Okay? So and the second reason is the bond strength. Okay? And this is bond strength coming from your orbitals. So what I mean by that is, for example, if you have this one, okay? Okay? This one over here. If you think about the hybrid orbitals over here, which will be sp2 in the sigma bond, under the top pi one here, and this one will be obviously what? sp3, because this carbon has 4, right? So this the sp2, sp3 they make the bond here. Okay. Okay. So and this one will be, this is sp2, this is sp3, because this carbon will have 2 hydrogen on it before. So later we're going to talk about this in more detail, but briefly explain do you see the sp3? sp3 means what? You have a 1 electron coming from the s orbital and 3 electrons on the p orbital coming down to make a hybrid, the same degenerate energy level for hybrid orbitals here. Right? You guys remember this? So that means sp3 has quite very high characteristic of the p orbital. Okay? Because there is a high proportion when you hybrid together. So you only have 1s, but 3 p electron were in the p coming down to make the hybrid orbital degenerate. So that makes the very high the p orbital characteristic hybrid orbitals. Then sp2, because there's only 2 p electron coming down to make a hybrid. So that makes this bond more s orbital character high, which is better for bonding, because the s orbital is the one obviously normally lower in the energy level, which is closer. So if you have a high in s character, the bond length will be shorter, because also the shape, but the reason is energy level should be the lower. So that is why the bond length between these two is very short. Double bond, you know that. So then, so if you have a held by this sp2 by these 2 sp3, will be a bit more stable than sp2 just holding on to 1 sp3. There's another sp3 not held by sp2. So that makes this one more stable than this one. It's just because you have a more number of the hybrid orbital held by a stronger bond, which is sp2. But there is only one here in this case, which is less substitute. This is more this di-substitute and mono-substitute. That shows how many hybrid orbitals are held by much stronger sp2 orbital in your double bond. So that's the second reason. Okay, so does it make sense? Okay, so to be honest, I'm not gonna put this on the exam. Only thing you have to know is this one. If it's more substitute, it's much more stable. If it's less substitute, relatively speaking, less stable. That's all you need to know. Okay, you don't have to know about this one, but this will actually explain why is it that way. Okay. All right, let's move on. But it makes sense though, right? For at least this stability trend, okay? That should be something I want you to remember for the exam, okay? Next one. So, here's, we're gonna do this one here, okay? So we have this one, okay? We have this one. So whenever I do this one, you maybe by now, you're just thinking this one, right? Okay. You should be looking at this one for sure, okay? So I'm not gonna do this every time, but make sure you guys do look at the same, okay? So anyway, so whenever you do this one over here, and this is what we did before, but this slightly different because this carbon is more with the R groups here. This is only with the hydrogen here. So what happens to here again, that remind you that the pair of electrons in the p or the pi orbital are more freely can be used for bonding. So they can pick up this electrophile, which is hydrogen here. So this will behave like a nucleophile, right? You guys remember this? And then when they grab this one, so they can actually grab two scenarios here. You have a two possible scenario, which is this one. Let me see. Okay, and you have this one. This one over here. Okay, so. The only difference from here, so you have the double bond, the one pair of electron on the p. We'll grab this one, and where you're gonna put this on, here or here? That's your question, right? So either this is going to be bound to here or here, because this is in the pair of electron between these two carbons. So you have two choices, this one or this one. Okay. So in this case, what happens to this one is this one. Because so you see that, right? When it double bond, not double bond, sorry, the pi electrons grabbing this one from the double bond, and then either gonna put it in here or in here. That makes the other carbon where you don't have hydrogen will be positively charged, because once there's a double bond, 4-4, but the hydrogen bond to this one, but this is missing one electron. The purpose it has in the pi bond, right? So this is now become positive. This is the same here. That's initially 4 and 4, but this will grab on here, this carbon. Then this will lose the one electron that were commonly shared in the pi bond here. This will become positive here. But between these two scenarios, this is the one happens, and then you see this only broken apart. So this goes to the bromine here, right? So this bromine anion. It become anion because the pair of electron goes on here, and this is become so it's electrophile grabs it. Okay, so this one onto here because this is now what looking for something positive. This is nucleophile now, and this is our electrophile. So they I think should go to attach because it's negative positive. You see that, right? Let's go here, attach to it. Okay, so now you can have. Okay. So you can see these two are from this one, okay? These two. But bromine always going to be positioned in this because of this is more bound to the more numbers of R groups over here. Okay. So this one, they only have a hydrogen, and this is the where the later this nucleophile bromine will attach to this one, because this is bound to the more numbers of R groups over here. Okay. So I'm going to explain. So if you have two scenario, so in chemistry, if you have a two scenario there, right, and then you're only going to have this one, so you can not do this one, so it won't be So there won't be this one, right? So there won't be this one. So because of this, you're only going to have this product, not this one, because you can't go through this process. Then we call this it's a radio specific. It's a specifically make only one type of products. We call this radio specific. And also it's governed by Markov-Nikov rule. So Markov-Nikov rule is one of the good example of radio specific reactions. Okay? Because it only makes the one scenario, one product out of two possible scenarios. And I'm going to explain why it's only happening in this way. Okay? I think. Okay. All right. So, but it makes sense though, right? So if you have a more substitute, more R group attached to that carbon. So this is a carbon cation, right? This is carbon and cation. Carbon cation. Okay. If that two possible carbon cation position, if that carbon cation has more numbers of the R groups on it, that is the way you're gonna put the later nucleophilic attack. So you're gonna have that bromination there. So I'm gonna explain why it is so radio specific on this Markov-Nikov rule. Okay. Yeah. Probably I'll do this more, obviously, on Friday. Don't worry about too much. I'll explain what type of exam problem we will see on the exam on Friday as well. Don't worry, but let's try to look at why it's happening that way, okay? So, if you have this one, okay? If you have maybe you can have this one, but okay. So if we have primary methyl, secondary, tertiary carbocation here, this is more stable. This is why you're gonna always locate the positive charge on this carbon with a more higher degree, because of the it has a higher stability. So if they can go through the highest stability, the good thing about this one is if it's happening in the stepwise, they can actually stop at the bit lower energy status. Okay, so they can actually prefer to be in the more stable form in the intermediate, so they can have another steps of the chemical reactions happening next. So I'll explain why this is stable than those ones. Okay, so here's the reason why. Okay. This is preferred because it's more stable. Why is it more stable? The first one is the first good reason is the inductive effect. Inductive effect. Okay. Inductive effect. So inductive effect, in fact, simply, do you know what induction means? Induction. So I'll try to explain the induction first. Okay. Let's try to talk about the induction. So induction simply means you have a certain type of compound looks like this. Okay, here. Okay, and then it's this. If you look at this fluorine over here, which is what? Very strong, highly electronegative, right? It's very high electronegative, right? And this one over here, right? And then also, if you look at this hydroxy group here, this hydrogen to the the oxygen to hydrogen here, oxygen is quite also quite high in electronegativity. Okay. And then the proton is not so high in electronegativity. It's even more like a positive than carbon. So what happens to this one? If you draw in more specifically, they try to withdraw the electron. Well, initially just covalent bond. They just try to have it, because this is a higher in electronegativity, this oxygen here. So they try to get the pair of electron will commonly previously share in this covalent bond onto them. So they become negative, and then they just release without the electron, because this is bit stronger pulling the electron toward when they break the polar bond. So they have the proton, which is the same as proton, right? Hydrogen cation is the same as the proton here, right? So this is behave like an acid here, right? See, this is when the oxygen, just take off the shake off the hydrogen cation. They take all the electron with them, so they actually donate not just hydrogen cation. So this is a good acid here. Just depending on how strong that acid is, depends on Ka. But anyway, this is what's happening here. But depending on not just the neighboring atoms here, but maybe one or another, you have also very highly electronegative elements bound to like next carbon. That still can affect the acidity of this compound, because this one is very high in electronegativity. So in this whole compound wise, this will help this oxygen or the other carbon to pulling the electron on this way. Then this oxygen will have a stronger force to detach the hydrogen without giving them electron. So if you change this one to just the methyl group, acidity of this compound will drop, because they don't have more additional help from other like some long distance still. But if you change it to something that is highly electronegative, that helps this whole compound detecting the hydrogen cation will be easier, because this also helps this grab this electron on this electron density in this whole compound. Okay, yeah, makes sense, right? So that's the induction. So it's not just about the atom to atom interaction, but all like in a whole. There's electron density wise in the whole parts of the compound. They can still have a certain amount of effect on how they can electron density can be able to move because of this. So not just for the neighboring carbons or the oxygen, but the oxygen will have additional force, additional strength to pull all the pair of electron to themselves to detach the proton, hydrogen cation. So they will be better acid. Okay. Okay. So it makes sense. So that's induction. Okay. So let's try to look at this one over here. So if I change this one to this one. Okay. So if you look at this one here, this carbocation with the positive charge is the carbon here. Okay. So which is kind of a, if you look at this carbon here for each. So hydrogen is lower in the electronegativity than carbon. So the electron density is more on here. So if you have a carbon surrounded by the hydrogen, because of the electronegativity, it's not so much different actually. It's just a little bit, it's a little bit different, but still carbon is slightly stronger to pulling the electron than the hydrogen. So they have an electron density more centered on this carbon surrounded by hydrogen. Okay, and then if you look at the carbocation position, which will be very electron poor, because it loses the electron there, so that helps to sustain the instability with this three neighboring carbon, because those carbons are relatively speaking stronger than pulling the electron to them among those three hydrogen around it. So there will be more electron density center. And those electron density going into the electron pro region, which is in the center, that makes somewhat bit more stable carbocation form. So technically speaking, carbocation is always unstable anyway. It's already unstable because it has a particle charge, which is not so favored by anything. But by some degree, this way is slightly better because of this carbon. Has a bit more inductive effects on here because those neighboring hydrogen is a bit more electronegatively positive that makes more electron density centered to this carbons and hold those carbocation with the particle charge a bit more stably. But this one, not so good because as you know, this is not so. That's so relatively speaking quite positive here, okay? And there are now inductive effects it can do. So this will make this positive, positive, positive mix very unstable. There's no neighboring carbon that can make it more sustaining. So anyway, that's the inductive effect. The other one is the same. As you can see, this is carbon here, right? So it has also carbon, hydrogen, sort of a hyperconjugation they can do with the carbon on this p orbital here. So they can also conjugate, hyperconjugate magnetism. So this is similar to what we discussed for the stability of the double bond alkene substitute alkene. Okay. So, but once again, only thing you have to know once again for the exam is if that carbocation position is more substitute with the R groups, that's bit more stable. Then they always choose that carbocation position to move on to the next step. That's why you have a Markovnikov the reaction happening on the one direction. That's the radio specific. Okay. All right. I'll promise I'll do this again on Friday. Okay. Don't worry about it. I'll do this again, especially for this one. I'll do this again on the Friday. Don't worry about it. Let's have extra credit.